Hi, welcome back. I got a question for you. Do you smell that? You know what that smells like? Some calculus. It smells like calculus. Sorry, I couldn't resist. We are going to start section 2, part A. We are going to start the free response questions. We are done with multiple choice. This is the 2013 AP Calculus AB practice exam that College Board was gracious enough to give to us. And oh man, we get to use a graphing calculator. Speaking of which, you already know. I use a TI-84CE, the color edition. Mine is such a cute, adorable, oh, there it is, mint green. I love it. They come in a variety of colors. I dropped a lot of links in the descriptions below because there are a multitude of colors. I bought my son the blue one because blue is his favorite color. Go ahead, grab one. If you already got one, no skin off my buttocks, friends. Let's start free response question 1. We got a graph, a shaded region. This is starting out good. Number 1 says, let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs y equals 1 minus x cubed and y equals sine of x squared, as shown in the beautiful figure above. Find the area of R. I mean, we get to use a calculator and everything? No way. Let's go ahead and do this. Okay, so first things first is when I integrate, that's how I find area under the curve, or in this case, area between the curves. Okay, we got this blue one right here. That looks like it is y equals 1 minus x cubed. And we have this one down here. That's going to go up here in green. That is sine of x squared. And we got this fancy pants little r here, this region. I got to find that area, okay? So the area between the curves, you always integrate the bigger minus the smaller. What does that mean? Well, the bigger curve is the one that's further away from the x-axis. So it looks to me like the blue, or the 1 minus x cubed, is the one that's bigger, minus, these ones he only goes to here. So that's a smaller one, the green one, which is a sine of x squared, okay, dx. Our problem here is I know I start from 0, my lower bound. I need to know this intersection point right here. Where is this on the x-axis? Guess what? I'm going to put it in a calculator and see where they intersect. All right, so let's open up this beautiful calculator. Let's see the detached LCD, because I know you guys, some of you guys have smartphones, and when I have the bigger screen, it shows up bigger on whatever screen you have for a smartphone, whatever. You know what I'm talking about. I don't got to explain myself to you. You're probably younger than me. You probably know a lot more about technology than I do. So let's actually use the same colors. So the blue, what I have on the board, is the 1 minus x cubed. 1 minus x cubed. Guess what? Can't use colors if you don't have the color edition. Oh, I'm so fancy. I'm so fancy. You already know. It's okay. The sine of x squared. Boom, it's right there. And we're going to graph these puppies. I don't want to, let's change my window. I really don't care to go much further than 0. So I'm going to go to negative 0.5 on the x-axis. I really don't care to go too much below the x-axis into the negative y, so negative 0.5. And let's graph this. Let's see what happens. Oh, my God. Oh, man, look at that. Oh, Lord. Look at all this. Oh, look at that fancy pants. Look at all that little green filth and flard and filth fluffing around. Now, obviously, I only need this bottom section here. Okay, I thought I was going to have this nice big boom and like this, and I'm going to be like, look at how cool I am. But, yeah, guys, that was disappointing. That's like when you're waiting for a large firecracker to go off and it just goes, and you're like, oh, waste of my time. So let's zoom box. And let's go down here. And let's gonna go down here. Yeah. Okay, right there's good. Go a little bit below. I'm gonna hit enter. Turns it into my little rectangle here. Go up. I only want to capture kind of where they intersect. Right there. So I'm gonna zoom in this box. That's what I wanted, my friends. That's what I wanted, my friends. So you can see we have the blue curve and the green curve, just like on our drawing here. This is our R region. I need to see this intersection point, specifically the X value. All right. So I know we're starting at 0. I just need to know what goes here. So in my calculator, second trace, and I'm going to pick intersect. I'm just going to move closer to the intersection point and literally just hit enter 3 times. 1, 2, 3. So this X value, you can see the bottom left of my LCD screen here. It's 0.7649722X. So this is what I'm going to do. I'm going to do you a solid, kid. I should probably store this. I got a feeling like this is going to come in handy later. We'll address it later. So let's take that X value right now. If I hit X, there it is. Let's put it in U for my upper bound. So let's store that into alpha 5. That's U. So anytime I do U, that's my upper bound. Okay? So now we'll call that 0.765. Let's round that 3 places for the sake of our problem. 0.765 right here. So my upper bound is 0.765. I don't need this anymore. I think you guys got the gist. It's the bigger minus the smaller. I'm just going to throw this in the calculator. And we're going to go, and we're going to have a jolly old time, St. Nick. So math 9 is the integration. From 0, and I suppose I can go for my upper bound. I could just hit enter there. Will that put it in there? Oh, it did. I could have put U as well. Parentheses, my bigger function minus my smaller function was a sine of x squared. How many open and closed parentheses do I have? 1, 2, 3, 4 open. 1, 2. First one. Second one. Third one. I need one more closed parenthesis, don't I? Bam. Dx. 0.533. Or we can round to 0.534. Okay, because the number after it is 5 or bigger. So that is approximately 0.534. That area between the curves right there. And that, my friends, is the answer. 1b. A horizontal line, y equals k, is drawn through the point where the graphs of y equals 1 minus x cubed and y equals sine of x squared intersect. All right? Find k and then determine whether that line divides R into 2 regions of equal area. Show the work that leads to your conclusion. All right. So first of all, let's do what we know. This in our calculator is the blue one, if you're with me for part 1A. This in my calculator is a green line that I graphed. We said this intersection point is 0.765. Does that sound familiar? Yep, right here. And now they're saying, oh no, we want to go forward. This point, okay, where does it cuts this in half? Well, it intersects at what y value? Look, I did need that y coordinate. So let's see if that's still in our calculator. Go to graph. Let's do our intersection point again. And now I want the y value of that intersection point. Okay, so we're going to go to math. No, I lied. Second, trace, intersect. And I'm going to hit enter 3 times. 1, 2, 3. That's 0.55. Let's call it 0.55235. 0.55 235. Point 55235. That's my K. Okay? Okay? Yeah, you see what I did there, kids, huh? So this is what I want to do. That's the value we found out. So find K. K is approximately 0.55235. That's part of the thing. Now we got to determine whether that line cuts my area into two equal parts. All right. Well, I know the overall area. Okay, the overall area is 0.534. That's the overall area of this R right here. Okay. So let's see, and I could pick either the top part or the bottom part. And what do I mean by either the top or the bottom? Highlighters. That does it all. I can take the integral or find the area, which is taking the integral of that top half highlighted in blue, or this bottom half that I'm highlighting in green. Okay, so I'm going to find those areas and see if they're the same. All right, so how do I do that? Again, let's start with the blue area. Okay, I need to integrate just like I did for the first one. Remember, it was the area between the lines, and I erased this. It was the bigger function minus the smaller function. All right, well, I'm going to do the same thing here. Okay, so I'm going to take just this blue area right here. The bounds are still the same from 0 to 0.765. So I'm going to integrate from 0 to 0.765. But now my bigger function is still going to be this one, 1 minus x cubed, minus my smaller function, which is the one that's not as far away from the x-axis, which is just the line 0.55235. I can write k here minus k and put dx, because that tells them, well, look, this is what k is. Or if I really wanted to, if I was a blowhard, if I wanted to really try hard and look impressive, which there's nothing wrong with that, you could put 0.55235 here, all right, dx. All right, so that's what we're going to do. And then we got to do the same thing for the green area. Okay, so let's get rid of these arrows. All right, so now I got to set up an integral for the green shaded area. Okay, it's an integral, again, from 0 to 0.765, 0 to 0.765. The bigger function minus a smaller of the green. This time, the bigger one is that y equals k, to 0.55235, minus the smaller one, which is this green curve, which is just a sine of x squared. Oh, come on, Visca, you can do better than that. X squared, there you go, dx. Let's figure out what these are. Let's see if they're the same. Let's see if that red dashed line cuts that area in half. If it did, the areas will be the same. They would be equal. All right, so, oh my goodness. Let's put that over to the side so we can see what we're typing into the calculator. Second, quick, let's go math 9. And we are going to go from 0. I'm going to cheat here instead of type that, from 0 to there. And we're going to do the one that's in the blue highlight. So it's going to be parenthesis 1 minus x cubed, parenthesis, minus 0.55235 dx. Now I'm going to bring this over here so we can see it. All right, so that's what I'm going to do. I'm going to hit enter. I got 0.25, I don't know, 7. Now I got to do the same thing. Okay, and again, I'm going to be a cheater. Put this in, but this time, I'm going to start. I'm just going to go back here and delete these. Delete, 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 delete. This is the bigger function minus the smaller function, which is the sine of x squared dx. Those are close to being the same, but those aren't the same. 0.257 and 0.277. Okay, I'm comparing these two numbers here. These are my areas. Okay, so it's approximately 0.257 and approximately 0.277. So to show the work that leads to conclusion, contusion. No, it leads to your conclusion. Okay, and I'm just going to answer the question. Does it divide the region into two equal areas? No. Not equal areas. Because we have two different areas. That's not bad work. It's the explanation and the diagrams and the showing. All right, that takes us time. It's not the actual math work. 1C, this is our last problem. There are only 3 parts to 1, A, B, and now C. Find the volume of the solid generated when R is revolved about the line y equals -3. All right, so I'm going to move this graph up here, and you'll see why in a moment. I'm going to go back to my calculator. I already have this in the table, okay? Now, I want to revolve this. Oh, look at those two little lovely red circles. I want to revolve this area around y equals -3, which is way down here, okay? So I'm going to change my window. I mean, window. Let's include a y minimum to -4 by 1. So let's graph that. Okay, here we go. This is all fancy. I'm loving it. And I really should go, oh my God, -3, I should go to 4. I should go to negative, it's like 7. But here's a line, -3. This is going to be rotated around 3. So this stuff's all going to come down here and rotate around it, okay? So just to give you that visual, which was, I'm going to draw it here anyways, dang it. Let's do this, like this. And let's continue this y-axis. Okay, let's say here's -3 for poops and giggles. All right, I'm going to take, let's draw a line. Yeah. Purple. I'm rotating around this line, y equals -3. All right, which means, remember, kids, in the graph, this is our green one. We've been doing this the whole time. And this is our blue one. Okay, and they cross at 0.765. Okay, and here's 0. Now I'm going to take this. Okay, and when my green function, sine squared, rotates around y equals -3, it's going to so it's going to kind of look like this. All right. And when my blue function rotates around y equals 8, it's going to go. So this function is going to kind of look like this. It's going to come up here and go, and it's still going to intersect at this point here. Okay. So this gray area, oh, this is going to be fun. Is going to rotate. And it's going to be down here, the rotation. All right. But the bigger part, the more important part is, look at the blue dash shape and the green dash shape. You see it makes a disc? It actually makes a washer, a circle with a hole missing in it, right? So what I want is the volume. Oh, I'll do this. The volume of the blue circle comes all the way around here, right? But notice there's a hole in the middle of it that's going to be cut out by the green circle, right? So I'm going to subtract the green circle, all right? So I want that blue circle, but then I'm going to take out this green circle, and that's what gives me that kind of washer shaped thing that I have there. All right, so let's go put that back there. Let's go put this back here. Yeah. Now, the $1,000,000 question is, do you remember, if I want volume, I integrate area. So, I'm going to integrate the area of a circle, which is pi r squared. Pi is a constant, it's going to come outside. So it's pi times my radius squared. All right, and yes, I know I need a dummy variable. All right, I need a lower bound and upper bound. It's still going to be from 0 to 0.765. So from 0 to 0.765. The question is, I'm not just integrating for one circle. I've got to subtract a smaller circle. So just like the previous problems, remember how we did bigger minus a smaller? Okay, for these ones, this was the bigger one. This was a smaller one. Okay, and then even in part A, we had the bigger minus the smaller. That was area. Volume is the same thing. Okay, so in this case, I'm going to take the bigger radius, which will be capital R, minus the smaller radius. Okay, I just got to figure out, obviously, just by looking at my graph, the blue circle is the bigger radius, okay? So watch. But what about this -3? Okay, be careful. My bigger radius, which I will do as a big R. Okay, normally, if I'm going from the x-axis, see this dot I'm creating? That distance is just 1 minus x cubed. But I'm adding an additional 3 spaces to it. I've got to go down 3 more. Okay? Yes, I know it's going to -3. But I'm at 0 and I'm subtracting, going down -3. When I subtract whenever I'm adding. So I've got to take my function and add 3 more spaces to it. So my big radius is 1 minus x cubed plus 3. That is going in for this r. And of course, I got to square it when I put it in. All right? Now let's look at the green radius. All right, all right. The same deal is going to apply. Get this out of the way. Get this out of the way. My radius, I'll do this in a dark gray. Yeah, why not? Dark gray. So my smaller radius, okay, normally my radius goes from here to here. I don't know if you can see that. I hope you can see that. That's just the green line, wherever the green line is. That's sine of x squared. But again, I'm rotating it. I got to go 3 more spaces down. So I've got to take my sine of x squared, and I've got to add 3 to that. All right, that's my smaller radius. Of course, I cannot forget to square that as well. All right? Now, good thing we have a calculator, because I'm going to integrate from 0 to 0.765. My pi is on the outside. It's my bigger radius, 1 minus x cubed plus 3 squared, minus my smaller radius, sine of x squared plus 3 squared dx. Be careful putting this into the calculator. We have done so much really, really nice work. It would be a shame to mess up at this point. On. Let's get out of here. Okay, I'm going to use this, because I don't feel like typing in that big, long decimal. And I'm going to go all the way to the beginning of this. And I'm going to delete it all and type it anew. So, okay, so I go back here. You'll see what I have right now is this. I got to put a pi in front of it. Pi. From 0, I mean, you see what I got here. It's pi from 0 to this big, long 765 decimal. And now I've got to go, oh, my God. It's going to be a lot of typing. I'm going to put this in. Okay, I mean, it's not horrible. Just get through it, for God's sakes. The calculator's doing the math. It's 1 minus x cubed. I pop off there and add 3 squared. I cannot for the square, minus my second radius. I'll put that in its own parenthesis. It's the sine of x squared plus 3. And I got to close that parenthesis, and I got to square that radius. All right, I think I have an opening and closing parenthesis for every parenthesis. Okay, open, close, open, close, open, close, open, close. They all match. Okay, sometimes you forget one and you get in there. My dummy variable is x, and I hit enter. 11.841. We will round that 0 up to a 1. That is approximately 11.841. We are done with 1A, B, and C. That was good. I like this. 25 minutes. That ain't too bad. That's with a bunch of explanations. If you're going to have to explain this stuff, whoo! I mean, we could have done that in, 5 minutes maybe. I don't know. It depends how fast you are. But with a calculator, it goes by real fast. You just need to know the methods. Bigger minus smaller. Free response question 1 really focused on the area between the curves, the volume between two curves when it's rotated. It's the bigger minus the smaller. That's a takeaway. And when you're doing volume, you integrate the area. I will see you when we do free response question numero 2, which is the last one we get to use a calculator for. I'll see you.